I'm the director of Indian Institute of Astrophysics. And as the name suggests, it's an institute which does astrophysics. So we do some things related to astronomy, astrophysics, and related areas. And we have the mandate of setting up observatories on the ground and as well as in space. So we do develop instrumentation for doing astronomy and do astronomy and also disseminate data and communicate it. So I'm here to tell you a little bit about why should we explore space and why I'm passionate about doing it for the last 30 years and what drives me. And so I'm assuming that you are able to see my slide. So do you see my second slide? Is it moving? Thank you. So astronomy, as I said in the beginning, and the panel, as part of the panel discussion, it has been driving us from the day one, like from our existence. Like we look up at the sky to look at the stars, the sun, the moon. So our culture, our festivals, are all centered around the phases of the moon. When there is a full moon, you have a festival, you have another festival, and there is a new moon. So we have been monitoring it, and our culture is centered around that, which means that we are an astronomy conscious culture. Not only that, we also have things like the stars of names. The Kritika, the cluster, the star cluster is very famous. You can see the Orion constellation, okay? So that was like for naked eye. You can look up, go outside in the clear night sky and look up at the stars and enjoy it. But can you, if you want to look at more deeper or a little better resolution, magnification, what do? So Galileo introduced telescope. So once we started looking at through objects through the telescope, we started understanding that, the Venus has got phases as well, the Jupiter has got moons, the Saturn has got rings, which naked eye cannot see. So which would mean that if you have a scientific instrument, you can see better. Now, from that day onwards, we have been devising a number of larger and larger telescopes and putting it up in special places where you can see the sky clearly and you have clear skies as well. So one such observatory is established more than 50 years ago is in Kavalur, which is called the Vainu Observatory, which is very near to Vellore. Now we establish it in sites where it is kind of away from the city pollution so that you can have clear nights. And also the light pollution is much less. I'll come to it a little more. So to summarize, ground-based telescopes have been the workhorses of astronomy research, and most of the things we know about astronomy is coming from the ground-based observations. Now, moving forward, we have, I think there is, I'm supposed to have a Mentimeter. It's not working. Okay, just open it up. So how many of you know that you can actually see lots and lots of stars in the sky? And how many of you think that actually you can see only a small number, but only telescopes can see a large number? All right, we have two sets of people who have both ways. When I was a kid, like the one who was sitting in the front, I could see a large number of stars in almost every night because the light pollution was very less. Now, from the same place, I cannot even see all the stars in Kritika cluster. You can barely see one or two stars, and is that Kritika? Actually, I have to guess. Now, what happened to all the stars? They got kind of completely dimmed because of the night pollution. Now, the question I face is that, is there any place where I can go and enjoy the night sky which is full of stars? The answer is yes. Where is it? So one of the observatories we have is in the Union Territory of Ladakh, which is the place called Hanle. And you can see a wonderful, I'm not sure with this light pollution around, you can't see the night sky. This is the problem, exact problem what we face in the night. This particular observatory is wonderful, and you can even see it in social media about, the Indian Astronomical Observatory. And these pictures are by our engineer in charge, Dorje Angchuk. If you're on Instagram, please, you can see Angchuk's pictures. They are amazing. And one of the pictures which I wanted to show you and explain is that the meteor shower, actually you can see originating from the Geminids. So it's amazing. So you can see the streaks which is originating from the two stars. So this is not a picture which is instantaneous, but throughout the night you take it and process it. So two things involved. You need a night sky. You need an instrument, good camera to capture it. 3, you need a software to process it. All 3 exist now. But the night sky is available only in certain locations. But you can capture it. So wonderful sky is possible, but that is the basis of driving not only science, art, and philosophy, the night sky. So many people have been driven by looking at the night sky, which we cannot see now, but that's a pity. So we should try to figure out where we can have access to beautiful night sky around every, city kind of a thing. And moving forward, now we have space-based telescopes as well, right? How do you explore space? You can explore the space out by looking through the ground-based telescopes or putting up a telescope up in the space. Now, what are the benefits and risks about it? The 2 telescopes which are shown here are big machines which are in India. The upper one is the 3.6 meter Devasthal optical telescope, which is in a place Devasthal near Nainital. The bottom one is the Vainu telescope, 2.3 meter in Kavalur. They're big instruments, big giants. So you need to have a large engineering team to make it and function it. And the VBT has been functioning since 1986, so almost 50 years. So if you want to make it function, making is one, making it continue to work is another one, and upgrading the technology is the third one. So huge amount of engineering goes on continuously, right? Now, how about space telescopes? Can you put up these kind of beasts up in space? No, that's not possible because they are very heavy to begin with. Second, you can't go and tinker it. Like, you make some mistake, that's gone. You can't go back and change it and replace it unless and until it is serviceable like the Hubble Space Telescope. It's very special cases. So how do you know that the things will work up in space? Believe it or not, these are stationary, up in the ground, well grounded. But your instrument is going to be up in space and moving. So you not only have to work, you need to control it, you need to make it work, get the data download. It's a very complex operation. So the risks involved are too many. And the experiments, you make it in your laboratory. And can I put the same experiment up in a space mission? Will it work? Not necessary, because things will fall off. Maybe the door hinges will not work because by the time it vibrates and go up, the door will vibrate and it will kind of break. The mirror, optics. You have to be carefully handling the optics. How do you make sure that the optics is not breaking? So we have managed to understand it, and all the tests you continue to do on the ground have to be multifold to make sure it works. So that is the risks with respect to space. But space also allows you to look at certain wavelengths where the atmosphere stops, right? So there's a necessity to go beyond the atmosphere, and also you don't get cloudy nights at all. All the time it's clear. So your efficiency builds up. So you have a risk-benefit analysis you have to do and prove that, yes, this is indeed important, it is impossible to do it on ground, then you put it on space. Now, where do we stand? So this is explained here on the graph here. I don't know whether you can see it, but the point is that the atmosphere blocks, high energy radiation. That is why life is possible. Life is continuing here. But such radiation does not enter the Earth, does not mean the objects out there is not emitting. So you have to put an instrument there to collect them. That becomes a necessity. The atmosphere makes a turbulence. So that also affects the data which is like the twinkling of stars. Basically, the twinkling of stars is because of that. So if you want to kind of confront this, you need to go up. But there are new technology like the adaptive optics does help in such a way. Moving forward, so the Great Observatories program of various space telescopes, including the Hubble Space Telescopes, was started by the United States, and we have several missions. And in India, it is the AstroSat, which is launched in 2015, which has completed almost 8 years, these are the space observatories. You know, the space telescope is one single instrument. Observatory would mean that you have multiple instruments up there on the same rocket, same mission, we can actually observe. So that is the difference over there. So this is what we have. Now, what does it do? The Hubble Space Telescope has helped us to look deeper in space because that helps us to look fainter, which would mean farther away things, and also redshifted ones. So you can look at far behind and then far deeper into what happened earlier. So that has been possible now. Now, what has gone as a next step? You know that the James Webb Space Telescope is there now. That is the first picture you saw on my title page is that wonderful picture from the James Webb Telescope. And you can read about a lot about the James Webb Telescope in the net, and a lot of information is available. I want to ask you one question. I don't think it is working, Mentimeter is working, but I talked about two space missions. One is the Hubble Space Telescope, which you all have heard about. The second one is the James Webb Space Telescope. Now you tell me, do you know which one has, it has got the main mirror collects the data and brings it to a focus, right? That's what it does. But the main mirror, how big can it get? Now, one of the telescopes, either the Hubble or the James Webb, uses multiple mirrors for the main mirror. Can you tell me which one? Hands up for Hubble Space Telescope. Hands up for James Webb. That's fantastic. So that is the first space telescope where we have used multiple mirrors on the primary. Can you imagine? We had struggled to make one single mirror act as a telescope mirror and make the whole light come to a focus precisely, accurately. Now we have multiple mirrors bringing all the light together to one point, not on the ground, but in space. So you have to be done precisely. You have done all the multiple mirrors without breaking up to a distance of L2, 1.5 million kilometers on the other side, opposite side, and make it work. So if James Webb is making a fantastic image of this universe, it's driven by equally challenging and amazing technology. So the takeaway point is, if you want to do cutting-edge astronomy and cutting-edge science in this area, you need to have totally amazing engineering and technology required. So astronomy is a technology-driven science. It works both ways. It's a positive feedback. Technology enhances the science. Science asks questions which are extremely fundamental, which the technology cannot deliver. It drives the technology back, saying that make it better, make it more precise, make it more accurate. So it drives back and forth. So astronomy is a wonderful example of technology and science and exploring the universe together. So yes, so this is the James Webb Telescope, which has got multiple primary mirrors. Now, where do we put these instruments up in space? So you have, so what you can do is you can put it in the nearby orbit, which goes around the Earth. Like the Hubble Space Telescope, it's about 300 kilometers. Or the International Space Station is about 300 kilometers. You can go up and come down and do the servicing. But is that enough? What happens if you have it in an orbit? It's very close to the Earth. The Earth will block some part of the observation, so the efficiency is lost. Now you can go up, you can go the other way because you can actually see it. The sun is on this side. It can go like this, so the solar panels can see the sunlight, but you can also see the night side, which is on the opposite side. Okay? But that's, sometimes you get the scatter and you don't really get the, full, the darkness. So where do you want to put it? The last slide shows you the Lagrange points. Which are the points which you connect two points, masses on both sides. Somewhere in the middle, depending on what masses you have at the end, there'll be a balance, gravitational balance, right? Now, if Earth is indeed small, and the sun is very big, so L1, the balancing point is very close to the Earth. Now, this point will be in between and also one on the other side. Similarly, the mathematics can actually prove that there are multiple points where the gravitational force can be balanced. The most important points are the L1 and the L2. Now, if you want to study the sun, you bring it in between the sun and the Earth and put it in between so that you have a non-obstructed view of the sun. if you don't want the sun, but sun is only for the solar panels, I know my telescope don't want to see the sun, like the James Webb, then you take it away and put it on this side. So you put it in this way so that it starts on sees the dark sky, but at the same time, the solar panel sees the sun. The solar panel should see the sun because that is the source of power. So there are certain boundary conditions you define a mission, orbit, etc. So that's how it works. I'll come to more about it when I talk about Aditya. Now, space also has an impact by creating data. As everybody is talking about data these days, astronomy has not only created, these missions have created a lot of data, they also have been disseminated through several websites, which anybody can access and download. They also provide you software required for it. So the benefit is you have data, you have algorithms which are already created, and anybody can work on it. So when I was starting to do my PhD, where would I get data? I have to go to an observatory. I have to work there. I have to work with somebody who's sitting with a magnetic tape, which has to be loaded in a machine, and then I read it. Only one terminal will read it. We'll be queuing to read our tapes. And then you print it out on a piece of paper and you start working on it, or you plot it on another one terminal. We have to queue up. So that was the situation in the 90s. Now the whole thing has changed because of developments in computer and also algorithm software. So you can hold a lot of data in your own laptop, but also in the cloud. Now the missions, like another mission is Gaia, which looks up the sky, all sky, and generates images as a very incredible rate. Now, if I want to do with a simple laptop, that kind of science, how do I do it? Now, the point how we do it is that the data archive holds the entire data. They also provide you some space where you can actually park the required data and make a small code to analyze the basic bare minimum requirement and download the required analyzed data to your laptop, which is manageable. So we are moving to that direction. It's made possible because the data structure is defined. Any telescope produces the data should be in this format. There should be metadata, which tells you these parameters, what are the things, conditions under which the data is taken. So you can actually do meaningful research, fully meaningful research. So this has also been an impact because someone else there capturing the data and doing something is not disseminating, equivalent to disseminating data and more people trying to do astronomy. So completely, this is called data democratization, has happened here. And why do we care? Every moment of our life is due to the navigation, because I don't know whether, no, there's no Mentimeter here. So the GPS satellites are giving you positions, right? But the satellite is moving, the Earth is moving, the entire solar system is moving. So how do we know where we are? And how do we take care of the precision from GTR? So science and the astronomy, basically the location, positioning information, and GTR at work every second to give us information. So science and astronomy and basic astrophysics is relevant in each and every moment in our life. So that is just to tell you that. Why should we do this? Why should we invest in so much of money out there? Second thing is we are all formed from stardust, and all the elements, where does it get formed? You know the periodic table? They all are formed in the stars, because the stars are the nuclear reactors, live nuclear reactors. And when they die, they kind of put out this dust around, pollute, in fact, and that's the pollution which results in other elements. So this is the kind of, we know the present day solar system composition. So this periodic table is a very special periodic table, tells you what element is formed from what type of stars. Each type of star has a role to play in the chemistry. So this all chemistry comes from various type of stars, various environments. It can be very cold to up to few Kelvin to million Kelvin, millions of Kelvin, etc. So astronomy is extremely relevant, and these are cooked up in stars. And I just want to give you a brief history of what we've done in India. So the observatory, like I come from the Indian Institute of Astrophysics. It dates back its origin to an observatory in 1792 founded in Chennai. It's called the Nungambakam Observatory. Then it moved to Kodaikanal in 1899. And it became Indian Institute of Astrophysics in 1971. The important thing which happened between 1792 and 1899, to give you a little bit of glimpse, is one of the eclipses in Guntur, where they observed it's a total solar eclipse. So everybody is out there to watch it, and you take a picture and the spectrum of the corona. That's when you see the corona of the sun. They found a line which is, nobody knew what it is. No idea what it is. What is it coming from? Why is it due to? Now, when the atomic physics and nuclear physics progressed, they realized that it is actually helium, named helium. Now, the helium name comes from helio. It's to do with the sun. The first time observation is from the sun, and it is from that. And now we have done many other set up various observatories. To name a few, we have the observatories right across the India, from Kavalur, Kodaikanal, which is our older observatory. And Kodaikanal Observatory is actually celebrating 125 years. And we also have, space programs like the UVIT, which is on AstroSat, and the Aditya, I'm going to talk about a little more. And the ambitious, challenging project of the 30-meter telescope. That is where you have about 500 segments, 492 segments on the ground. Like the James Webb was on the space, we have it on the ground. It's a 500 segment. And India is making about 100 of them in Bengaluru. So that is a really challenging project for the next 10 years. And these are some of the observatories, pictures. Now, coming to the newsmakers of last year, one was the Chandrayaan mission. The second was the Aditya mission. This is not the mission to the sun. It is the mission to study the sun, which traveled about 1% of the distance from Earth to the sun. Okay? So I just want to clear the doubts of it's not to the sun. You can't go to the sun. And I have a question now. The question is, I have to guess the question as well, sorry. So the question is we have been studying the sun, right? We have been living with the sun. This is living with a star. How many of you consider sun as a stable energy source? Wow, okay. How many of you consider the sun to be a dynamic energy source? All right, that's really encouraging. So that's indeed nice to hear that we have been taught through a sun as a stable source, and sun is not a stable source, and we can see that from our data collected from Kodaikanal, 800 years of data which is made public now. You can see the solar cycles, which is up on the front one, so top one. You can see the solar cycles are not actually the same. That means the sun is not equally active whenever there's an activity period. Now we are going into the activity period, so we will see more of the solar flares and sunspots, etc. So we know that the more studies are also coming up. So sun is a stable source in terms of energy, but the outer part is not stable. I should make myself clear. The sun is actually in hydrodynamic equilibrium. There's no problem with that. The problem is with the outer layers where there is a magnetic reconnection, the material flows. It's called the coronal mass ejections. That is where it is dynamic. Internally, it is stable. Now, so PSLV, it is launched, and it has actually reached the L1 point. And now we have developed something called a coronagraph, which makes if you want to study the corona, you have to block the disk, because the disk is exactly like, trying to figure out that plot out, my slides out there, because, it's too bright. So the disk is too bright. You have to block the disk light to see the corona. How do you block this disk light? You can actually put a block. But the problem is you have to collect the light. The sun is too bright. You can see how hot it is here. So if you're actually collecting the light, the instrument gets really, really, really hot. So you have to manage the thermal, but at the same time collect it. So there are a lot of challenges out there. And so I just don't want to. So these are the kind of instruments. I just wanted to give you a glimpse of our instruments. So this is a complex instrument, the chronograph. You can see how many number of optical elements are there. And the challenge is to make every optics not break, not move, and the electronics function, and give you exact data, how exactly you wanted it in your own laboratory. Up in space, 1.5 million kilometers away. So that's a big challenge. So we've done it. We have powered on our electronics. They're all working fine. We're just about to open the door to get the chronographic images. So these are some of the pictures, and these are the lab experiments we have done. And these are some of the lab we have. We have the Space Sciences Lab, which is in our Hosakote campus, which is an end-to-end. You can actually do from designing to actually doing everything, and then doing the shaking, baking to make sure that it survives and deliver. So this complete thing is there. It is available to space startups to develop their own payloads. We are actually having collaborations in many cases. And we are also doing the 30-meter telescope project. The industry is heavily involved in it. These are very highly contributing in kind, the mirrors, the segment support assemblies. A lot of industry is participating in this. And these are some of the pictures of the high tech we have there. And we are also into more ambitious projects. Some of them are here. So I just stop here with the things of, we have no idea what we are working on. Most of the time, the projects which we come across are completely first of its kind. We have no idea how to do it, but we figure out how to do it. For dissemination of science, we are also opening up and we are setting up a planetarium in Mysore, which is actually a planetarium where the whole dome is full of LEDs. It's not an inner dome. It's like the LEDs you see. And the dome is full of LEDs. You can actually pass on information to each and every pixel in the dome and make it more dynamic, make it more high resolution images can be done there. So you can actually do science communication extremely well because you get the immersive experience. So that is the idea here. So this will be open towards end of this year in Mysore. You're all welcome to come over there and experience the wonderful, the first of its kind in the world planetarium. Thank you.
Thank you. Thank you so much. Can we have a huge round of applause, please, for Professor Subramaniam right here? I think we ended the presentation on a wonderful note saying, you know what? Scientists might not always have an idea of what's happening, but they are trying to figure it out. And that is where we're going to leave this presentation with. But on that very, very exciting note, I think all of us are also going to book our tickets to Mysore to see the planetarium put together. And now, please raise your hands if you have questions for Professor Subramaniam. Okay, so we have one hand here in the blue. The mic is coming to you, and you're welcome to ask. And then we can have one hand over there. Yeah, right there. Yeah.
Good morning, ma'am. Ma'am, my question is, as you told, there are many times there are solar ejections by the sun, and due to that, there are many solar storms and solar flares. Then how does the space observatories survive that?
Okay, so your question is, one of the objectives of this mission is to find something called space weather. Space weather, you know that what is the kind of particles out there and how much toxic it is, how aggressive the particles are, how energetic the particles are, how to make your electronics and how you make your solar panels survive. So when you go to large distances, we do not know those kind of environments. So we have models, but we need precise estimations, number one. Two, how to make it work. We have to space harden them before they send it up. So these are pre-preparations done before the launch of this instrument.
Thank you, ma'am. Ma'am, first of all, thank you for coming here and enriching us with your knowledge. I just wanted to ask a very different question. So when we speak about space, astronomy, astrophysics, right? Most of us, and even the younger generation thinks, okay, America, NASA. How does India actually give us more, what is the vision India gives, and why the people or why the young generation in India should invest in the education and the missions here in India? I mean, what do you suggest? Which is better for the young generation, India or US from a future perspective?
There are a lot of opportunities coming up in India with respect to space science, and also the startup, there's a number of space startups which are doing things which are outside ISRO as well. So there are a lot of opportunities in India. Like the government has actually sanctioned 2 mega science projects in astronomy itself this year. So LIGO, which is the gravitational wave observatory, is going to come up here, and the square kilometer array is also going to come up, and that's not in India though, but we also have the 30-meter telescope project which is going on. So what I wanted to mention is that you don't have to do exactly science, but as the astronomy is technology driven, we need people in all engineering fields, starting from mechanical to optical to electronics to computer to data science to software to everything. So it is a large team involved. So if you want to have a machine like JWST up there, and if India's vision is to put a multi-mirror telescope out there, we need an entire team out there. It's just not me, just not the scientists. It's a large teams of passionate, willing to accept challenges people.
Thank you for such a wonderful talk. I really enjoyed it. I have a question related to, I've read that your research is extended to the accretion disk around the which leads to the formation of planets. So I have read that accretion disk is a part in the black hole. So what do you throw some light how it can lead to the formation of planet?
Yeah, so basically it's like, how your question, which I can put it in a broader context, is like physics applied to astrophysics scenario. So this is basically fluid dynamics physics. So fluid dynamics it can be cyclone, similar fluid dynamics. It can be an accretion disk around something. You actually have to model it as a mass, and gas is modeled as a fluid. So how does the fluid go around anything? So it's many things, and many basic physics things and theoretical physics applied to astrophysics can be applied to many wide range of applications. Magnetic fields, it can be anywhere. So same kind of physics works. So that's the thread which is, going from physics to astrophysics.
Thank you.
Hello, ma'am. Thanks for the talk. I would like to ask a question that for all the youngers here, that how can we get into IIAP? Because Indian Institute of Astrophysics is 200-year-old organization, and I'm really fortunate to be a part of it for a couple of years for Celioscope. So this is my first question. Second question is how solar physics is more prominent field for research area right now. Thank you so much.
Yeah. So the first question is, how can anyone get into IIAP for various, let's say, internships or PhD or whatever? So when I introduced my institute, I did not say what kind of educational or academic programs we have. We do develop observatories and run them and, do the space instrumentation. We are an autonomous body under the Department of Science and Technology. We are not a university, and we cannot grant degrees. So that limits us to take on undergrad or postgrad programs, and we have to be accredited by a university to grant degrees. So we run only PhD programs. So it's not a very big university, so we can't handle too many students. But if there is an aspiration, we have to grow in that direction. It is indeed interesting, but then right now we are limited by these. But we do have internship programs where about 100 students do internship throughout the year.
Right. Thank you, ma'am. We just have time for 2 more questions. So maybe let's, that one.
There's one kid right in the front.
Right.
We have this question from there.
Absolutely. So the last question.
We have probably the youngest astronomer of this audience.
Yeah. Okay. So
aspiring astronomer.
Yeah. Please go ahead at the back, and the last question to you. Yeah. Go ahead.
Good afternoon, ma'am. I have a question that can the dark matter be used for our profit in the upcoming years?
Can you repeat it? Dark matter can be what?
Can dark matter be used for our profit in the upcoming years?
For profit?
Yeah.
Okay, I haven't come across this particular thing. First of all, we do not even understand what it is. We don't even understand we can harness it, and what is it? Is it profitable? Then we think about profit. Right now, we are thinking about mining in, moon and or maybe in asteroids, which can be useful. But then you again have to do a cost-benefit analysis where you going there, the whole expenditure of going there, mining it, and bringing it back. What are you going to gain? So that is being done now, but in future it'll have definitely a bright future, but not not in that dark matter as yet. And there are many questions. I'm going to be around. You are welcome to talk to me and offline, and we can do the discussion. No worries. Yeah.
I have a question.
Sure, please go ahead.
Why does time slow down near a black hole?
Oh my, it has to go a little slower. What to do is like stuck in the traffic. Though you want to go forward, you can't go, right?
Thank you for your question. And a huge round of applause for Professor Subramaniam, please. Thank you so much, Professor, for taking out time for this talk. It was really lovely.